all about chemical equations. Hopefully, you've done a lab experiment and you've seen some chemical changes that have taken place. Here are some things you might observe: bubbles, color change, a solid forming, heat or light given off. That's sometimes really cool. Flames, popping sounds. These are all different clues that a new substance may have formed. Reactants are the starting materials in a chemical reaction. They will be written on the left side of your arrow. Products are the substances newly made in a chemical reaction. They're written on the right side of the arrow. Let's make sure you understand some of the symbols that we use when we write chemical equations. The arrow itself can be read as yields, makes, forms, or produces. It's kind of like the equal sign in an equation. S, or a downward arrow, means solid. The downward arrow is likely there because when a solid forms in a test tube, it will often sink to the bottom of the test tube because it's more dense than the liquid it's in. G, or an up arrow, means a gas is formed. Think about, where do the bubbles go when they're formed? They usually go up because they're less dense than the liquid they're in. L is for liquid. This is an L, sometimes mistaken for an I. You might find it helpful to write the L in cursive. AQ stands for aqueous. It means that chemical has been dissolved in water. The water is not necessarily taking part in the chemical reaction, but it had to have water to dissolve the compound so that it could do the reaction. A double-headed arrow like this one means the reaction may be reversible. That means the reactants may form products, but then the products may break down into the reactants again. If you have something written above an arrow, it can often mean these are catalysts that are applied to help speed up a reaction. The Greek letter delta that looks like a triangle means heat is being supplied to the reaction. So either you're heating it on a hot plate or with your Bunsen burner to make the reaction take place. That's what you commonly do when you bake a cake. You mix all the stuff together, but it doesn't turn into delicious cake unless you bake it, so you're supplying heat. Sometimes a chemical catalyst is used, and we write that whatever the symbol for that catalyst is, like XYZ above the arrow. Manganese dioxide, which is a common name for MnO2, is often used as a catalyst to speed up the decomposition of hydrogen peroxide into oxygen gas and water. That's just one example. Platinum and palladium, I think, are also often used as catalysts in industrial processes. So sometimes you might have a little PT right here over the arrow, which means platinum is being used. And a little charge mark like that means, guess what? Electricity is being supplied to the reaction. We can actually hook up a battery with some electrodes and put those electrodes down in the chemical solution and cause chemical change to happen. A chemical equation is what we use to describe what takes place in a chemical reaction. It's a combination of chemical formulas that represents what occurs in a chemical reaction. Let's look at this chemical equation. You've learned how to read the chemical alphabet. Those alphabet letters are element symbols. And you've learned how to read some chemical words, the nomenclature of compounds. Now it's time to learn some chemical sentences. If I read this chemical sentence, it translates to say, 4 atoms of solid copper. How do I know they're atoms? Because what's the representative element of copper? Or the representative particle? Copper is an element, so the representative particle is an atom. So that's 4 atoms of solid copper. I know it's solid because of the little S at the end, right here. This plus means reacts with. This is oxygen. This is a diatomic element, And the representative particle of a diatomic element is a molecule. So this 4 atoms of solid copper reacting with 1 molecule of oxygen gas, notice it's a G for gas, forms, yields, makes, produces 2 formula units, because copper 1 oxide is an ionic compound, so these are formula units. It makes 2 formula units of copper 1 oxide solid. That's how I read that chemical sentence. What are the big numbers in front? Well, the big numbers are called coefficients. A coefficient is a number placed in front of a formula that tells the number of atoms or molecules that are used in that chemical reaction. If we go back to this slide, this 4 is a coefficient, this 2 is a coefficient, and do you know what coefficient is here? It's a 1. It's not written down, but we understand that there's sort of a ghost 1 right there. So why do we have to balance equations anyway? We balance equations because the law of conservation of matter says that in a chemical reaction, matter is neither created nor destroyed. That means we aren't creating any new atoms, and none of the atoms are going away. Notice this is not in a nuclear reaction, and that's a whole different ballgame. These are ordinary chemical reactions. When you put gasoline into your car, you burn it. The chemical energy in the gasoline is converted to thermal, mechanical, and kinetic energy for motion. Where does the gasoline go? Why do we have to keep putting gas in your gas tank? Because the gasoline is reacted with oxygen to form carbon dioxide and water. Here's the chemical equation that represents the burning of octane. This is a combustion reaction, and you can tell because it's a hydrocarbon reacting with oxygen to produce carbon dioxide and water. In this equation, the atoms of the reactant molecules react and rearrange to form new product molecules. The number of each type of atoms remains the same. I'll have to show you how we count it to prove it, but this is called a balanced chemical equation. Here's how you can keep track of how many atoms of each kind are in an equation. You can call it a RAP sheet. RAP for R-A-P, reactants, atoms, and products. So first you want to make a list of the atoms. I would go through and write down carbon, hydrogen, and oxygen right here under where it says atoms. And then count how many are on the left side and how many on the right. Don't forget we multiply coefficients times subscripts when we're counting. So for example, I would do carbon first on this one. Where'd my pointer go? So I have 2 times 18, 2 times 8, 16 carbons on the left side of the arrow. And on the right side of the arrow, I have 16 here, and there's a 1 understood here, so that's 16 also. The 2 does not apply to the carbon. The 2 only goes to the oxygen. So that's 16 and 16. The hydrogen has 2 times 18, 36, on the left side of the arrow. And on the right side, look at that. 18 times 2, also 36. And lastly, let's count the oxygen. 25 times 2, 50 oxygen atoms on the left side. And on the right side, I have 16 times 2, that's 32. Plus, I have 18. This 18 applies to the hydrogen, but also to the oxygen. So 32 plus 18 makes 50. So at the end, the left side of the equation equals the right side of the equation. Not that the carbon has to equal the hydrogen or the hydrogen has to equal the oxygen, but there's 16 carbons on the left and 16 carbons on the right. 36 hydrogens on the left side and 36 on the right, and 50 oxygen atoms on the left and 50 oxygen atoms on the right. That makes it a balanced equation. Another name for this is taking atom inventory. That's when all the reactant and product atoms are counted and placed into a chart. That's the rap sheet I was showing you. Here's a chance for you to practice. Let's look at this equation. This is silicon dioxide reacting with carbon to produce silicon carbide and carbon monoxide. Is it balanced or is it unbalanced? Well, let's count and see. You have one silicon on the left side. How many silicons on the right do we have? One. We have two oxygens on the left. How many oxygens on the right? Oh, we only have one oxygen. And let's check carbon anyway. One carbon, one carbon. Plus, oh, here's another one. There's two carbons over here on the right. So this equation is unbalanced. So what you should do is make an atom inventory. So we counted silicon, one on the left side, one on the right. For oxygen, two on the left and one on the right. And for carbon, one on the reactant side and two on the product side. So we can see that it's not a balanced equation because one matches one, but two doesn't match one and one doesn't match two, so it's not balanced. Now, in this equation, we want to try to balance the equation. So what we're going to do is add coefficients to these blanks in front. Do you remember how much work we had to go to get these compounds written correctly? You are not allowed to change the subscripts anymore. Now we can only change the coefficients, which is these big blanks in the front. So maybe you look at this and say, well, I can see that there's two oxygens on the left side and only one on the right. So you can maybe fix that by putting a 2 as the coefficient on the right side. That makes two oxygens here and two oxygens there. So now the oxygen is happy. However, that changed the number of carbons. Carbon is 1 here plus 2 more. That makes 3. So what number do we need to put on the left side to fix the carbon? A 3. So update your atom inventory. Now let's check and see what we have. One silicon, two oxygens, 1, 2, 3 carbons and 3 carbons. So now it's all updated. It's now